Alright, last section of this chapter. We're looking at rational functions. So on the previous video, I talked about how a rational number is an integer over an integer. Rational kind of always means take the almost simplest object and divide by the same type of object. So in the world of functions, polynomials are kind of the most basic functions. So if you have a polynomial divided by a polynomial, this is a rational function. So if that's a poly and that is 2, then this is a rational function. You can see where we'd have some issues, domain issues, because we do have a denominator there. So the things that we're trying to look at are zeros. Now, if p of x divided by q of x is 0, I can multiply through by whatever q of x is. And I still have 0 over here, and over here I have p of x. So we get zeros when the numerator is 0. When the denominator is 0, one of two things can happen. If when I factor the top and the bottom, then I can cancel it out, then cancel out the 0, then that makes a whole. If I can't cancel out that factor, then it makes an asymptote. So real quick example, if I had, say, x squared minus 3x plus 2 over x squared minus 4. So it's a polynomial divided by a polynomial. I have issues, domain issues, where x is 2 or x is negative 2. But I don't yet know if they're asymptotes or wholes, so I first have to, no amount of canceling takes this out of the definition of the function. This is there, so these are issues. I cannot plug in these two values. But when I factor this, I get x minus 2, x minus 1 over x minus 2, x plus 2. So this one gets canceled out, which means this one, which came from the one that remains, that's an asymptote. This one came from the one that got canceled out, so this one is a whole. So a hole in the graph is just you're going along and then you suddenly have a hole like that. An asymptote, we have 3 different kinds that we'll consider. We have a vertical asymptote, which you've seen before in 1 over x. We normally dash them. Let me change color here. Oops. So that you can see the dashing since it's going to be on the axis. So if I'm graphing 1 over x, then when x is 0, that does not cancel out. There's no x in the top to cancel it, so I have an asymptote there. I also actually have a horizontal one, but 1 over x, you should recall, looks like this. So it approaches this line, but it never crosses it. The same can be said of this horizontal asymptote, which I'll talk about in a minute. The horizontal asymptote could be crossed infinitely many times, not by a rational function, but by some functions. The horizontal asymptote can be crossed. It's just that you eventually approach it. So any size of little interval around it, eventually I'll land inside that interval and never get out of it again. So if, for example, there was something that went like this, where those kept getting smaller, it would cross infinitely many times, but it would keep getting closer and closer to the asymptote as it went out. So from the denominator equal to 0, so numerator equal to 0 leads to zeros. Denominator equal to 0 leads to wholes or asymptotes, vertical asymptotes. We have two other kinds of asymptotes. We have horizontal asymptotes, and then we have slant asymptotes. This isn't all that exists in the world, but this is all that we're going to talk about in this course. So for the horizontal and slant asymptotes, you're looking for end behavior. So what you want to know is, how do the numerator and denominator compare to each other? I'm going to choose an example that has, I'm going to choose two examples that have different types of horizontal asymptotes, and then I'm going to make one that has a slant asymptote. You could kind of solve for them in the same way, but we really consider them differently. So horizontal asymptote, let's say, for example, that we had the function something like that. Then the technique that we're going to use all the time comes down to this. You know that 1 over x, as we go off to the right or the left, gets close to 0. As x gets big, we're taking 1 into more and more and more and more pieces. So this approaches 0 as x approaches infinity and as x approaches negative infinity. So this arrow means approaches. We could also use this regarding a vertical asymptote. If I had a function that had an asymptote here and did this, well, because it's in the middle, it's not an end like this, it might go differently on either side. So in this case, we'll say this is a. As x approaches a from the left, I put a minus sign up there, it means from the left, f of x goes to infinity, because it just goes upward forever. On the other side, it goes to negative infinity. So as x approaches a from the right, f of x goes to negative infinity. The right word is approaches. I often say goes to. That's sort of the same. But anyway, if I have 1 over x, or 1 over x to the 5th, or 1 over x squared, or 1 over x to the whatever, as x goes to infinity, the bottom gets larger, and the top never does, because it's 1. Or even if it's 4, or 5, or 12, or negative 8, whatever it is, it doesn't change in size. The thing on the number of pieces it's getting chopped into is increasing without bounds, so the size of each piece is going to 0. That's for plus or minus infinity. So again, a horizontal asymptote is trying to tell you what's happening toward the end. That's also what a slant asymptote does. They both talk about what happens as x goes to infinity or negative infinity. A vertical asymptote talks about what happens when x goes to an undefined point. Okay. So in the case of this function here, to show you the reason this works, I'm going to go through and do a process that they often have you do, and then I'm going to tell you what it then comes down to. So in this case, the highest power is x to the 4th. So I'm going to divide through on top and bottom x to the 4th. So this equals 4x squared over x to the 4th minus 7x over x to the 4th plus 3 over x to the 4th over 5x to the 4th over x to the 4th plus 3 over x to the 4th equals 4 over x squared minus 7 over x cubed plus 3 over x to the 4th over 5 plus 3 over x to the 4th. We just said that a number over x to a power goes to 0, so this goes to 0, this goes to 0, to 0, to 0, and that's 5. So 0 plus 0 plus 0 over 5 plus 0. The only thing that gets to survive is the 5 because it had the highest degree, so they canceled and it got 5. Everything else ended up going to 0. So when I looked at this to start with, I could have said, okay, well, everything's going to go to 0 except that the guy who's growing fastest. So, oops. So this will go to 0 plus 0, or minus 0, plus 0 over 5, plus 0 is 0 over 5. If instead I had f of x equals 4x cubed minus 7x plus 3 over 5x cubed plus 3. Now what I would divide through by is x cubed. So these two would survive. These would go to 0, so this would be 4 minus 0 plus 0 over 5 plus 0. So when these degrees are different, if the bottom is a larger degree, like it is here, then the only thing that survives is a number in the bottom, and so the whole thing goes to 0. In the case where the degrees are the same, the only things that survive are the leading terms of each. So they both stay. If the degree on the top is higher, if the degree on the top is higher, so like 5x cubed minus 7x plus 2 over 4x plus 3, this goes to, this is the only thing that survives, 5 minus 0 plus 0 over 0 plus 0. But 5 over 0 is a problem. We don't know how to answer the question, if I have 5, how many nothings do I have? So this is some kind of infinite. We don't know if it's positive infinity or negative infinity without thinking about it a little longer, but what I do know is that it's not a horizontal asymptote. It's either shooting off to that direction or this direction, infinitely. So it does not plateau into a horizontal asymptote. So I'm showing you basically the three situations for horizontal asymptotes. We want to compare the degrees. If the degree is bigger on bottom, then the horizontal asymptote is at 0. If it's bigger on top, there's not a horizontal asymptote. Later when you take pre-calculus or calculus, don't tell them that your algebra instructor told you that there was not a limit. It could be an infinite limit, it's just not a horizontal asymptote. And then if it's the same, then you take A over B, where these are the leading coefficients. There's a little mnemonic, Bobo Botten eats DC, that has to do with horizontal asymptotes. Bigger on bottom, 0. Bigger on top, none. Each are the same, divide coefficients, and that means leading coefficients. So Bobo Botten eats DC on horizontal asymptote. The only thing now that's left for us to talk about is slant asymptotes. A slant asymptote happens when it is going off infinitely, but in a straight line. As far as in behavior, it doesn't follow the line, but it eventually approaches the line. This only occurs, that's weird that I did that, only occurs without an E when the degree of the top is 1 bigger than the degree on the bottom. So remember, if it's bigger on top, there's none, but if it's bigger on top by 1, then there's slant. And the way you find this one is by dividing, straight dividing. So on vertical asymptote, you're finding where the denominator is 0 and making sure it doesn't cancel out. Horizontal asymptote, you're just comparing the degrees. And then slant asymptote, you have to divide. Let me give myself plenty of space here. So for a slant asymptote, let's say that this was x cubed minus 9x plus 2 divided by, say, 3x squared plus 1. You would do long division. So x cubed plus 0x squared minus 9x plus 2, because remember, you can't have any wholes, just like you wouldn't if it was 1,000 and, well, the negative 9 makes it a problem, but pretend that was positive, we can compare it directly. If it was 1,092, you would put the 0 to indicate that 100 spot, so that's what we need to do. Same thing over here, 3x squared plus 0x plus 1. X cubed divided by 3x squared is all we do to start with. So x cubed over 3x squared is x over 3. The 3 stays in the denominator because we don't have anything in the numerator to cancel it, and x cubed over x is x. X cubed over x squared is x. So that's x over 3. So I multiply it through, and I get x cubed. X over 3 times 0, x is 0. X over 3 times 1 is x over 3, and then I subtract this. So I get nothing there, 0 x squared minus 28 over 3x, and then I bring down the 2. That's not going to actually matter because I'm only going one more step if I'm doing this in practice, but to make a point for you, I'll continue. So 0 x squared divided by 3x squared is 0. So I multiply 0 through, and down here I'm left with, writing too low, okay, bring this over here. I'm left with negative 28 over 3x plus 2. So the point then is that I could have rewritten the original function, the original division, as I took this, I just divided what was divided. This was a fraction. So I can rewrite the whole thing as x over 3 plus negative 28 thirds x plus 2 over 3x squared plus 1. Normally you'd have a plus b. I should have built this so that we did have 1. We would normally have a number here. In this case, we just happened to get 0 because of the way that I chose the functions. But anyway, now this part is bigger on bottom, 0. So this thing goes to 0, so the whole thing goes to x over 3 as x goes to infinity. So I have a slant asymptote at y equals x over 3. That's my linear piece that the function approaches. So this is how you find a slant asymptote, is by dividing. Now let's get to some of these. We want the domain of this function. Domain is going to always be determined by the denominator because the numerator I can plug in anything I want. So the only thing I want in interval notation, the only thing it can't be is 4. So x minus 4 cannot be 0 because x minus 4 is the denominator. So x cannot equal 4. Which means I need to start at negative infinity and go up to 4. Open parentheses because I don't want to include 4. And then also go from 4 to positive infinity. Okay, so this one we want to find the horizontal asymptotes. So you can go through and divide everything by x squared if you want, or you can look at this and say the degree is bigger on bottom so that it has a horizontal asymptote at 0. It has one horizontal asymptote. Okay, so now our question is, if we know that y equals 0 is the horizontal asymptote, does it get crossed? The answer is usually that it does not. But sometimes it does. So in this case, what we would do is set this function equal to 0. But remember, if I set it equal to 0, I'm really looking for the numerator to be 0. This numerator is 6. 6 is not 0. So it actually doesn't ever cross that. We want to identify asymptotes here, vertical, horizontal, and slant. So kind of step one, we would factor everything. This top doesn't factor, it's already a line. So let's look at this part. We see 4 pieces. We would try grouping. In reality, we would want to, we would end up having to use some of these rational theorems, rational roots theorems and Descartes signs and things like that. But this is probably going to group. This looks to me like it's going to group. So if you have 4 pieces, you might as well try grouping. Always try the easier things first before trying to dig out roots. So we would factor out x squared. Then we always factor out the minus, and we can also factor out 4. And now we factor out x minus 3. But now we have a quadratic, so we would still want to keep factoring. In this case, it's a difference of squares. This isn't a thing. That's a scribble. Okay, so this is what we have as our denominator, so that q of x equals 3x plus 1 over x minus 3, x minus 2, x plus 2. Okay, so as far as horizontal asymptotes, bigger on bottom, 0. That's all we have to do. We would not have a slant asymptote because if it's bigger on bottom, then it's not bigger on top by 1. The only way you check for a slant asymptote is if you don't have a horizontal asymptote at all, And if you don't have one at all, then you just check the difference in the degrees. So slant asymptote, we would not have one because we have a horizontal one. Vertical asymptote, we would have everywhere that these things are 0, provided they don't cancel out. You can see we factored this and we weren't able to cancel anything out. 3x plus 1 doesn't cancel any of those. So at x equal 3, x equal 2, and x equal negative 2, all. So it has 3 vertical asymptotes, 1 horizontal asymptote, and no slant asymptotes. The vertical are at 3, negative 2, positive 2, and the horizontals at 0, Okay, so this one we want to sketch a rational function so that it has a horizontal asymptote at 3, a vertical asymptote at 1, and those intercepts. If you were asked to sketch this on paper, there are literally infinitely many functions that have these values, but you just have to find one that works, so we need to put 0, 4, and 4/3 0 in there already. And then we need a horizontal asymptote at 3, and a vertical asymptote at 1. So then, to do the simplest possible thing, we would just approach both of these asymptotes and pass through there, and approach both of these and pass through there. Okay, so first we want to sketch the horizontal asymptotes. Y equals 3. X equals 1. And then the intercepts 0, 4. Oops. 0, 4. Four-thirds 0. And then, because we know, going back, there are asymptotes, and these points are here, so we would know we need to pass through 0, 4, which this one does only, actually. But then you'd also want to check the 4/3 0, and here is the graph that stays on its correct quadrants and has all the proper plots. Is that A? Okay. For this one, we want to graph it. So we still would go through the same process we just went through. So first I'm going to factor it. The top factors as x plus 1 squared. And the bottom is just x, so nothing cancels. Horizontal asymptote. Bigger on top, none. It's bigger on top by 1, so we will have a slant. We'll go find that in a minute. And then Vertical asymptote, this x doesn't get canceled out, so when x is 0, we have a vertical asymptote. So vertical asymptote at x equals 0. Okay, now I'm going to get that slant asymptote. So x squared plus 2x plus 1 divided by just x. X squared over x is x times x squared. So those go away. I've got 2x, bring down the plus 1. 2x over x is 2. And at this point, you can stop. So before I continued so I could argue why the remainder doesn't matter. So hopefully now we accept that the remainder doesn't matter. So y equals x plus 2 is our slant asymptote. The remainder goes to 0. That's what I mean by it doesn't matter. So you don't have to consider it for the slant asymptote. Now, we need x-intercept and y-intercept. So y-intercept, we plug in 0. That's undefined. We have this vertical asymptote at x equals 0, so no y-intercept. X-intercept is when the numerator is 0, which means x plus 1 is 0, so that only actually happens when x plus 1 is 0, x is negative 1. So no y-intercept, x-intercept 1, negative 1, 0. Okay, so vertical asymptote 1. Horizontal asymptote, none. 1 slant asymptote. The vertical asymptote is at x equals 0. Slant asymptote is at y equals x plus 2. It has one x-intercept, no y-intercepts. X-intercept is at negative 1, 0. And then we want to find it. So we need an asymptote at x equals 0, which they all have. We also need an asymptote at x plus 2, which these two have. These two, so when you do a slant asymptote, basically what we have here is we need to graph x plus 2. So it passes through 2, that's the intercept, and then the slope is 1. So if I go over 2, I go up 2, kind of like that. So I have an asymptote like that. And then I've got a negative 1, 0 here. And I also have a vertical asymptote at 0. This is my only intercept at all. This is likely to hug like this. The fact that it was x plus 1 twice does mean it bounces off. We talked about that before. So it bounces off there and should stick close with both of those asymptotes. And then up here, we can't pass through this, so we've got to be up in this corner. you can plug in 1 and find that that's 4. You can pick anything. Anything on this side of the asymptote will get you a point over here. And then that's going to look like that. Okay, so that's how you graph them kind of from scratch. So over here we would be looking at these two. This is the side the zero's on, -1. There's no 0 over here. This one has a 0 at +1. So 0 over here, so it's B. Okay, so for this one, we're given the number of citizens of voting age in a certain country in millions. This is a model for it. This is another function which represents the number of people who voted in millions. So this is who can vote, this is who did vote. We want to write the function defined by V over N and then decide what it means. So we get 1.04t plus 35.1 divided by 0.0138 t squared plus 1.03t plus 73.8. And what this is the number of people who voted divided by the number of people who could. So if I said, oh, 100 people were able to vote and 50 people did, if you took 50 over 100, that's the proportion of people who voted who were able to vote. So it's sort of the percentage turnout. Well, not percentage, proportion turnout. So that's how this is interpreted. Okay, so P of t equals don't know how to make that subscript go away. Hopefully it won't hurt me. So the percentage kind of, you'd have to multiply by 100 who voted. Now we want to plug in 60. P of 60, so we just plug in. .04 times 60 plus 35.1 divided by so 0.526. P P of 60 means, so it's within T years of 1932, so that's 1992, 60 years later. The amount, I was supposed to round to 2 decimals, 3. The percentage of citizens who voted was 53. All right, last one. So on a calculator, sometimes you want to set your window to something that makes sense so that it includes all of your important information. The standard viewing window goes from -10 to 10 on both x and y. Okay, so we have one, well actually no. Okay, so let's take it over here, let me show you. Oops. For our vertical asymptote, the first thing we have to do is factor. So if we factor the top, we get x minus 2, x minus 1 over x minus 2. So this actually cancels, so it's a whole. This graph will look exactly like the x minus 1, except it'll have a hole at 2. So no vertical asymptote. And we want to look at the different windows that it's suggesting. Okay, I didn't want to make you watch me pull up the calculator again. So y equals x squared minus 3x plus 2 divided by x minus 2. So currently I'm in the standard window. The standard window goes from -10 to 10 in both x and y, and if yours is not set that way, you can just reset your RAM and it will automatically do it. So here it is. And what happened is it just passed by 2 without so much as a blip. We don't know what's happening at 2. It looks, for all the world, like just the line x minus 1. There's no indication of anything else. So let's go back to the window and change it to get closer to where x equals 2. So instead of this, we're going to go the x min negative 4.7, oops, negative 4.7, 4.7, still of a scale of 1, and then negative 3.1 to 3.1. So this is doing two things. It's getting closer to that point at 2, 1, but it's also scaling it so that the scale is the same in both directions. Well, I honestly still don't see it. Maybe if I had a calculator this would work. I'm going to change the window one more time. Okay, so hopefully in your calculator, when you put it on this window they suggested, you could see that little gap. It's very likely it's just my software. So hopefully with the first window, you could not see the gap, and with this one you could. But if you see that little gap right there, that's where we would normally draw a little circle. That's a hole. And it otherwise just looks like x minus 1, kind of like we expected it to. So I'm going to choose what I assume was their point here, and that completes this section.